All right, welcome. We're going to do section 13.5, which is curl and divergence. Okay, so you see these terms thrown around a lot. They're pretty valuable once you start talking about doing calculus in space, then you need to have these concepts. Okay, and they're usually also together with one other one that we've already been talking about called the gradient. So let's talk about that first. The gradient. Now, the gradient acts on scalars functions. Okay, so that's like some w equals f of x, y, z. So you get one singular number out. Okay, and it's just the gradient of f equals, and you get out a vector. Partial with respect to x of f, partial with respect to y of f. Let me extend that a little bit. And then partial with respect to z of f. Okay, so that's the gradient, which we've already seen. Okay, but it's good it goes with these other things. Now, next we're going to talk about actually the divergence, even though alphabetically it's not the next one. The divergence actually acts on vector-valued functions. Okay, it's a key distinction. It acts on a different kind of thing. Okay, and we write that. So let's say we have our f of x, y, z is, let's write it this way, p of x, y, z, q of x, y, z, r of x, y, z. Then the divergence is the gradient operator or the derivative operator taking a dot product with f. So that's going to be partial with respect to x of p plus partial with respect to y of q plus partial with respect to z of r. Okay. You might also see that as written as the divergence of f. Okay. Actually, let's do that here. Just like up here, you might have seen this as like the grad of f. Particularly older books use that notation. Okay. Finally, the curl. The curl also, it again, acts on vector-valued functions. Okay. The curl, the curl of, let's say, f, you might denote it as the gradient operator in a cross product with f, which in this case, well, the determinant, we're going to put I, j, k up top, the derivative operator in the second row, and then the vector valued function in the third row, and then we'll take the determinant there. So the I coordinate is going to be partial with respect to y of r minus partial with respect to z of q. The j component is going to be partial with respect to z of p minus partial with respect to x of r. And then the k component is going to be partial with respect to x of p minus partial with respect to y of q. Okay, so that's the curl. Let me... Okay, now there's a nice little theorem. A vector field is conservative if the curl is 0. Okay? And that makes sense if you think about it. Because what did we do? We actually did this on the last section. If it's conservative, that means it's a gradient function, right? That means that f is the gradient of f for some scalar function. Okay, and a lot of the vector valued functions that you see in physics are conservative. They need to be. Okay, that means, let's take for example, that means that p is the partial with respect to x of f, q is the partial with respect to y of f, and r is the partial with respect to z of f. So let's take, just for example, this component of the curl. Okay, so let's do it over here. Partial with respect to y of r minus partial with respect to z of q is going to be partial with respect to y, but r is partial with respect to z of f, minus partial with respect to z, and q is partial with respect to y of f. So these should be 0 by the whole thing about mixed partials being equal. For, let's call it, well-behaved. Okay, all right, that's it for now. We'll get some problems in the next video.